Well, thank you everyone again for joining us tonight. This is the fourth and final presentation in our AFI SOFA seminar series. Again, for those who have joined us previously, thank you so much for coming along and dialing in tonight. Again, we are delighted to present part two of Professor John Campbell's presentation, or an extension perhaps of what he shared with us a fortnight ago. For the new people, I will just quickly give you a brief bio on Professor Campbell. He's an author, a physicist, has 2 master's degrees and 2 doctorate degrees. He, in his own words, has written far too many papers, patents and books. We were discussing just one of them previously. He became a foundryman apparently by mistake, which, you know, is understandable. He has bulldozed foundries, he has built foundries, he has run foundries, he has owned foundries, and he admits to making some really bad castings along the way. Nevertheless, he is keen to make better castings and promote the cause of better castings, improving profits and the industry as a whole. Without further ado, I think I will hand over to Professor Campbell and we will start tonight's presentation. Thanks very much.
Well, thank you, Amber, and good evening to you all. It's very much good morning here, but I'm slowly waking up, and I should be getting up to speed as we go. So somewhere down here I have a share, and I'm going to see whether we can get some success. Well, doesn't look too bad so far. Yeah, it's looking good. So there's hope for us yet. Well, it's a pleasure to be speaking to you again. During the course of the talk this evening, I'm briefly going to recap where we are. It's very important to keep in mind the principles that we're talking about. But then we'll move on to the new stuff. And frankly, the new stuff is, well, it's mind-blowing. It's so important. And it shows how important profession is, that it's going to influence the whole of engineering and much of the world. So here we are. This is where our casting technology is today. We're pouring things. We're folding in this surface. We're making these double films like cracks in the liquid, and we're making bubbles. These are the 2 entrainment defects. And these are the kinds of things we're doing when we're impinging other drops on the surface. We impinge in a biofilm. When we fold over the surface, we fold in a biofilm. Whatever we do, biofilms are the result, and they are cracks. They are cracks in the liquid. And this is what we have to do if we want to avoid them. This is the way we should be filling castings. We should be gating them so they're actually filling uphill inside the mold. And then we have a chance of making a really good casting. So these are the 2 major defects, the biofilms and the bubbles. This is a little classical experiment of mine, many years old now, whereby this is first poured with solidified in air, and these tiny shadows you see are the convoluted biofilms. This is where my piece of paper has been screwed up into a little ball because turbulence has raveled the biofilm into a small defect. But the defect can open up, and here is the same liquid poured at the same temperature with the biofilms now opened by simply reducing the pressure in this case. But there are lots of different mechanisms for opening biofilms. And what you can see is they're huge cracks and they fill the liquid. I mean, this is a useless bit of metal because its properties are going to be so bad. So these are the same metal poured at the same time, the same temperature. This has compact biofilms that have raveled. This has unfurled, opened biofilms, which are really dangerous in terms of properties. Okay, and then of course you remember that on the backs of biofilms we get precipitates. This is an aluminium silicon alloy, but these things happen in steels and nickel base. They happen all the time. The precipitates form on biofilms. Interestingly, for those metallurgists amongst you, precipitates don't form on grain boundaries, I've concluded. They only form on biofilms. So they precipitates appear to form on boundaries, but only when there's a biofilm in the boundary. So, there it is. Know whether that's true, but I'm pretty sure it's true. So here we are. This is a fracture surface, magnesium alloy. Just horrendous great folds of a large biofilm here. However, this side, which looks like a bit of, I don't know, bit of bread or biscuit or something, something edible. But this too is just covered in biofilms. I mean, there is no metal to be seen here. It's all oxide all over this surface. And here we are again. There's again the same magnesium alloy. These oxide films are just amazing. And this one where we made a small casting. This is about a 100 by 200 length, a simple bit of slab casting. This is in pure aluminium. And this is done at the right speed where there was no entrainment. This is done where there was some entrainment. And you see these huge cracks. These are centimeters long. There's one here, there's another one at the back. They are massive cracks which can now form. And when you think this is pure aluminium, and we should have been able to bend this piece of casting and tie a knot in it without any defect appearing. And here we've got cracks in something as ductile as aluminium. There's something deeply, deeply wrong somewhere. So these biofilm cracks explain. Hello, I seem to have competition. Okay. The biofilm cracks explain things which would be very difficult to explain by conventional metallurgy, because conventional metallurgy would say pure aluminium cannot crack. It's not possible. So here we have, here we have a nickel base alloy. This is the CY40. I don't know whether any of you know about it. And here on the surface, the rather blunt cutting tool has torn open the biofilms, so you can see them everywhere. I mean, it's a bit of very bad turning, I have to say, but it's also a very bad casting that it's full of so many biofilms. And here's another CY40 casting where the biofilms are much larger now, fewer of them, but they're just huge in size, centimeters long. So let's move on now and look at the control of both microstructure and the mechanical properties by biofilms. See, as a metallurgist, and I look towards castings, I've been brought up to say that the microstructure controls the properties. And more, I've come away from that point of view. I now look upon it as the properties that are mainly controlled by biofilms. And whereas I used to think that they were controlled by such things as heat treatments and such like, and clearly there is quite a lot of control by heat treatments, but there's even more control by biofilms. So biofilms explain a lot and are very, very helpful to our understanding. And this is one of the mechanisms which happens with biofilms, that they get, I don't know whether you can see my cursor, but as the dendrites grow, they tease out and elongate and straighten biofilms, and they push ahead. The remnant of this great heap here is being pushed. But this straightened biofilm now becomes a straight crack, like an engineering crack, and so becomes really extremely important in terms of properties. And here we've got this is a 6mm diameter tensile test bar, and what you can see is that the biofilms have been pushed ahead by grains growing out from this direction and grains growing out from this direction. And this heap in the middle here, this is a heap of spare biofilm that's just finished up as this central mountain range. And this is out of the same casting, but this is a bit of the casting that's solidified more nicely. And here it's just covered in very tiny biofilms. These biofilms are large because of a big wave which happened at this side. But in this part of the casting, there are no big waves, and these are just the natural population of biofilms controlling small cracks. And here's cast iron with so-called plate fracture of ductile iron. I mean, this should never happen, that we get brittle fracture of grains like this in ductile iron. But it happens because of biofilms. And when we slice the structure and look at it, these are the lines of the biofilms. I mean, this is just an amazing structure, which you'd have no hope of explaining without some knowledge of biofilms. So let's get on to the meat of what I really want to say today. This is the theme of my new book. And I say, let's look at this inclusion, which might be a carbide in a steel. And very often the carbides in steel sit at grain boundaries, and very often they're cracked. And the failure modes of steels are accepted nowadays as extending the cracks from cracked carbides. And so this crack goes off into the steel and causes the failure of the steel. So when I ask any normal metallurgist, or I can ask you all, what's the logic here? What occurred first? And you would say, well, there's the sensible way to interpret this will be, here is our inclusion. The inclusion sits probably in the grain boundary, and then the grain boundary is stressed and the inclusion's brittle. And so, whoops, I need to go back. So the inclusion is brittle and the inclusion cracks. So the logic is we start with the inclusion, we provide stress, and finally the inclusion cracks. It's a 1, 2, 3. Now it's interesting. I'm going to tell you now, that's completely wrong. The reality and the way to describe this scenario of the cracked inclusion is the logic is this, that the crack is there first. The inclusion grows on the crack, and stress is never involved once. Now, what you can see is that the thinking of our metallurgy starts to be absolutely reversed. So here we've got the normal logic of inclusion first, applying stress, which results in a crack. And now we're going to reverse this logic, saying inclusion was there first. Sorry, let me start again. The crack was there first. There was never any stress, but the inclusion grew on the crack and therefore appeared to be cracked. And there's no doubt that logic 2 is correct. We now have lots and lots of evidence. And this evidence is only a repeat of what this very famous physicist called Griffiths, is an Englishman, worked at our National Physical Laboratory over 100 years ago, and he predicted that in every case of the failing of metals, the cracks were there first. The cracks pre-existed. So the logic 2 we're showing here is just a restatement of something that's been around for 100 years from our famous scientist called Griffiths. And when we look at the Daisy. When we look at engineering metals and we lay them out according to their properties, their elastic properties as it happens, right from ductile going right through to the most brittle metals, what we see is that most metals are ductile. Nearly all of our engineering metals are ductile, with a few in an intermediate situation here, but very, very few are brittle. And you can see these are the metals we don't use in industry, because simply they are brittle. They fail suddenly. And it's important we know what's happening here. And what's happening with our ductile metals and what makes them ductile, the very nature of ductility, is that if there is a crack, say we put a hacksaw crack into some ductile alloy, like say an aluminium alloy here, and we put our hacksaw crack into that, and then we try to open the hacksaw crack. As we open it, the crack doesn't extend. What happens is, microscopically, at that stress point, the crack puts out dislocations. And the interesting thing then, of course, is that it suffers plastic deformation. And all that happens is the crack opens and the crack gets wider and wider and blunter as we're opening the crack. The crack does not extend. It doesn't grow. It just gets blunt when we apply stress. And that's different to brittle metals at the other end, where if we put a hacksaw cut into those, if we could, and try and extend it, it extends as a crack. We don't get our extensive plastic deformation. It doesn't blunt, it just propagates. So keep those two fundamental differences in your mind, because when Griffiths here, our famous English scientist, 100 years ago, when he thought about how cracks extended, he wrote down a little theoretical equation based on energy. It's been a very good equation. Huge amounts of our understanding of cracks has come out of this. But there was a second chap. This chap, Barenblatt, what a name. He's a Russian, and I don't know whether he's still alive, but until quite recently, he was still in his Russian Research Institute in Moscow. And he did a crack model as well. And his model was a fascinating model. He considered the solid, and he considered that there was a region in the solid which had no cohesion, surrounded by a region of strong cohesion. Now, when you write out whether this is going to propagate as a crack or whatever it's going to do, interestingly, we come up with the Griffiths model. So these two models actually give the same answer. But this model, where we have a region of our lattice now with no cohesion, surrounded by a region of strong cohesion, this is a bifilm. It could not be a better model of a bifilm. And so I was very, very happy to see this, because here a bifilm model by this clever Russian has given us the same mathematical solution to cracks as Griffiths did 100 years before with a rather different energy model. So what it means is our bifilm modeling of the start of cracks and of the initiation of cracks has a really fundamental scientific basis. And I can't tell you how proud and relieved I was at that point when I realized that bifilms had come home. They were now respectable, and they now obeyed all the logic and all the mathematics of standard crack equations. Okay, so let's move on and talk about the different ways in which metals fail. So let's deal with the very simplest way of all, where we just put a tensile test bar in a tensile machine and we just pull it until it gets overloaded and it breaks. This is pretty simple stuff, but you can see what happens when bifilms get in the way. This is back to our CY40 nickel base alloy, which we've cast beautifully badly, just cramming bifilms into it, because this is the world's most rotten running system I ever saw, and I played hell with the foundry and said they deserved what they got. They never did it as badly again, and now they can cast test bars that look beautiful and have decent elongations. Well, actually, this had a decent elongation, but not by plastic flow, but by opening of bifilm cracks. So you can just see it's just an unbelievable kind of situation in which the bifilms are totally in control of this overload fracture. So let's move on to some more interesting mechanisms. So let's just talk about creep fracture for a moment. And I want to talk about, you may have heard me talk about this particular result before, where we're looking at the amount of creep deformation now with time along here. And if we have our ordinary equiax casting, and I should tell you before we go on, this is a nickel-based super alloy that for this result. Cast in vacuum, incidentally, of course. So if we look at our standard equiax casting, a normal casting with normal grains growing randomly, and we just pour it in a standard turbulent manner, so we create bifilms, and now we grow grains in amongst the bifilms and the grains expand as they grow. And as the grains move, they push the biofilms ahead. And finally, of course, the biofilms become trapped between opposing grains. And so the biofilms finish at grain boundaries automatically. And so this equiax casting would have biofilms at practically all of its grain boundaries, all over the place. And so now we put it into a hot environment where we put it under stress, and lo and behold, it hardly extends much at all. And after a very short time, here, bang, and it comes into two pieces because the biofilms open out, slowly deform, and the whole thing falls apart. Now, if we don't make it as an equiax casting, but if we slowly solidify the casting from the bottom and we slowly move our crystals uphill over a period of an hour or so, we can push biofilms ahead so that a single crystal turbine blade grows by pushing the biofilms ahead out of the casting, and such that the single crystal has very few biofilms left in it. And that's the reason for this enormously different performance in terms of the amount of creep and the length of time that this will last. I mean, it's an order of magnitude better properties than the equiax casting that's full of biofilms. This performs well because it has very few biofilms. Interestingly, it still goes bang. And so up here at the point where it finally fails, it finally comes apart. And that's interesting because it tells me that there are still some biofilms in there, and the single crystal process didn't get rid of them all. Nearly all, but not quite. Still enough to cause it finally to fail. See, if we'd been successful to get all of the biofilms out, the answer is it would never fail by fracture. It would keep on extending and extending and getting thinner and thinner, and would finally come apart at the last atom, but it should never fracture. Okay, so you can see there's terrific potential for affecting the creep of metals. And just in case you were thinking that, maybe that's a bit of a one-off, let's talk about this situation in which we're going to talk about now heat exchanger steels. And I want to tell you about the new creep theory of Brian Wilshire. I don't know whether any of you know Brian. He was professor of metallurgy at Swansea University. A great larger-than-life man with a great booming voice. We could just about hear him up in Birmingham. But he proposed a new interpretation of the creep equations. And whereas all those metallurgists amongst us will have learned that there's three parts to creep. There's the initiation, there's the steady state, and then there's the final transient. Brian said, this is rubbish. There's only two parts. There's an initial transient and a final transient, and where they overlap appears to be the steady state. And what he did was to derive equations for the initial transient, an equation for the final transient, and this gave a fantastically improved way of predicting creep lives for certainly for steels, and maybe it's good for other things too. I wouldn't know. that what is interesting from my point of view, and taking up Brian's theory that we've just got two parts to the creep curve, the final transient will almost certainly be the opening of biofilms. And if you say, well, if I get rid of biofilms, what's going to happen? Then we won't get a final transient. And in fact, what will happen is this part of the curve disappears, and all we'll get is an initial transient, and after that, nothing, basically. So we extrapolate our initial transient, and now we find the thing never failing. Now, this hasn't been proven yet. I'd love to see someone attacking this and seeing if we can't prove it. And this should happen for all our heat exchanger steels. It would mean that our heat exchangers in power stations and as well as nuclear stations, and they would last maybe 5 times as long. It would transform the economics of making electricity. So this is an enormous important prediction, which I'm just loving to see someone confirm if they can. So let's move on again. And let's now talk about fatigue. Fatigue is something that worries me a lot. I want to talk about 3 different aspects of fatigue, or 3 examples. I want to talk about the failure of wind turbines, aero engines because of turbine blade failure, and helicopters. And this is deeply tragic, the way a helicopter falls out of the sky because we got our castings wrong. We shouldn't be doing this. We shouldn't be supplying to the world bad castings. And so these are all serious and pretty tricky. The wind turbine, I guess we just deserve what we get here. You see, the wind turbines are designed for a 20-year life. And so the main bearing of the turbine, the huge bearing which takes the main weight of the blades and is subject to massive stresses. These, I say, are designed to last for 20 years, but quite a number of them, a high proportion, are failing after 5 years. And this is threatening the economics of wind power because it's so enormously expensive to lose your turbine after only 5 years and have to dismantle it, take the whole thing down, rebuild it, put it all up in the sky again. So this is one of those things which shouldn't be happening. I write to Siemens and say, I think I might be able to help. But they write back and say, we know what we're doing, get lost. And so I say, the lives of their bearings at the moment is something that, as I say, we deserve what we get. And here is the contact surface of a typical bearing. And this is the typical structure underneath that surface, which has been viewed as fatigue cracks generated by the rollers which roll over the surface. And these rolling stresses, repeated rolling stresses over the surface, they're all at something like 2 gigapascals. I mean, the stresses are horrendous. So it's not surprising that these things finally, great chunks of material fall out. and get into the bearing, and then the bearing does a macroscopic disintegration. But the interesting thing for me is to see that these cracks are, of course, completely misinterpreted. Remember that Griffiths would say the cracks are there first. And here he is, he's right. These cracks are here first. They're put in by us, the foundry people. And these are the cracks we put in by the turbulence of pouring. And this arrives in this particular steel, in the way the steel is cast. It's top poured into an ingot. That gives huge turbulence, of course, putting in many biofilm defects. And then the ingot is forged and is pierced through the center, and the center's opened up to a ring. And so that the biofilms are concentrated in the center of the original ingot by the grains growing inwards. And so all that concentrated load of biofilms in the center are now around the center of our ring forging. And what happens now is that if we can, I don't know whether you can see this, but we have a small area here where there's just something going on right in the center there. And if we look at our next slide, here is the next slide. And in the center there is an inclusion. Now, it's not very clear on here, but there are little kind of wings either side of this inclusion. And there's various white etching cracks. So there is an event going on here, taking place, which is a real fatigue event. And so what's happening, if we go back, here is a tiny, tiny fatigue event taking place, where the fatigue crack is moving out step by step, making beach marks to give its progress by progress, cycle by cycle, extending. So there's an extending crack in here that's fatiguing away. And probably at other places throughout this network of biofilms, there are little fatigue events going on which are linking up these big blocks of material, which then once the little connections go, because the connections are now subject to massive overloads of stress. Once they go, then this whole section here will jump out into the bearing and start to trash the bearing. And so the wind turbines are failing because of the very poor casting practice in steel making operations. And I say it serves them right. They should get some decent casting practices in place. And I'm fed up with talking about it. So let's move on and talk about this compressor failure in from a single blade that broke, but took out most of the other blades as it went around. And this was part of a little engine in a Cessna, which then subsequently crashed and people were killed and terribly seriously injured. So it's quite a tragic failure. But here is the blade and a section through it. And what you can see are these interesting features. These are bifilms. And the original fracture surface is this surface here. This is the mounting medium used by the metallurgist. And you can see the oxide film on this surface. And you can see here There's another, that's probably a bifilm. You can't see the two films. This is definitely a bifilm. You can see the two films here. So frankly, all these things, this one, this one, this one, they're all bifilms. And what's more, they're parallel. These are pretty well parallel. And this is a hallmark, a distinguishing feature of bifilms. You remember them growing because of the way the dendrites move. And so as the dendrites progress, they straighten the bifilms between them. And this is an instance where we have, oh yes, here's a better view, where we have a single grain here, and bifilms must have grown in this direction. And so here we have our bifilms flattened out in crystallographically flat areas. So this is a kind of facet on the fracture, and these would have been facets if it had fractured here but didn't. But the fact that these are parallel tells you this is a bifilm. Now, it can't be that these are cracks by stress. These are not generated by stress, because once one crack is generated by stress, parallel cracks then can't form, because this is now stress relieved. The stress is dissipated by the first crack. A second and third cannot form. So, whereas a bifilm doesn't care about that. It forms just because no stress is involved. So these are definitely bifilms. Here we are again with the same fracture surface. It looks chaotic, but in fact, these are dendrites we can see with an overlying oxide, which is the bifilms again. And what's more, you can see cracks at right angles going into the structure. And this is again typical of bifilms because, you know, they're not just straightened out on one plane, they're straightened out on planes at right angles. They're not like ordinary planar engineering cracks. They go off in all directions. So this is a typical bifilm failure. And again, it's just a great that the world of making turbine blade manufacturers still to this day cast relatively poorly, and so we still have bifilms in turbine blades which should never be there. It's a great pity, and it's time we stop doing this. Now, let's move on a little bit. Just talk for the moment about corrosion and bifilms. And of course, if this is a bifilm, these are some of the precipitates that form on bifilms. They like to form on the bifilm because the volume change and the shape change are easily accommodated by the gap between the two films. And in doing so, the precipitate here actually prizes open the bifilm a little bit. So as these grow and they prise open the bifilm, so you get corrodant sucked in. And the corrodant now can corrode very, very readily because this is a really good corrosion couple, or if this isn't, this is, you know. So there's a good chance of having very active corrosion couples. And so corrosion happens from the inside of our metal because the bifilm is in. So what happens then, of course, is that particularly the entrance here grows significantly. And here we are, we formed an etch pit. And here we are with our bifilms. And again, if I was wearing my standard metallurgist hat, I would have said, oh, this is very strange. An etch pit has led to cracks. Well, that answer's wrong, of course. The cracks were here first, and the etch pit forms because of the presence of the cracks. So again, the cracks are pre-existing. They're put in by us foundry people, by the way we cast our metals. So the etch pit is merely telling you that there's a bifilm emerging at this place. So the etch pit is a tiny defect, but the crack can be enormous at the back. And it's that has to be feared, not the etch pit itself. So I'm moving on now to talk about helicopter failures. And in particular, I'm going to talk about vacuum arc remelted steels, VAR steels, the most expensive steels you can buy, the most difficult, long-winded, extended process known to mankind. Anyway, you start with an electrode up here, you pass a big current through it, it melts the tip of the electrode drop by drop into an ingot down below, which solidifies. But as it solidifies, we get cracks. Now, these cracks are known about. In fact, if you were to take this ingot and try to forge it, it just cracks. It cracks straight through. And that's despite the fact that this would be, say, a nickel-based alloy, which can't crack because it's ductile. Okay, if you have a crack in it and you try to extend the crack, it won't extend, it just blunts. But here we have a nickel-based alloy, say, in which when we go to forge it, it cracks right through. And just the ingot will often fall into pieces. I mean, this is not a trivial failure. Anyway, how does this happen? It happens because as the ingot is built up and the liquid metal spreads around, it spreads in this fashion as a sideways, horizontal progressing meniscus, which gradually will fill up all this area and then we'll restart a new meniscus which will travel again and spread out. And so you get this layer by layer accumulation. And of course, inside the vacuum of the vacuum arc process, there's plenty of oxygen. And so, of course, this layer and this previous layer oxidizes, gets an oxide film. Also, the little layer here, which is rolling over the top, that has its oxide film. And so we have a substrate oxide, we have another oxide rolling over the top. And so that we're coming together to make a double film, a double oxide film, which is, of course, a bifilm crack. So we generate huge bifilm cracks by this process. Now, just by going back here, what you can see is I've got a peel depth here. There is some of these cracks are machined away. They're ground away or they're turned away to a depth of about 5 millimeters. However, although I show this crack just a little further out and a little further out here, it's only just recently I've come across evidence whereby these cracks are up to probably up to 50 millimeters deep. So we got 50 millimeter deep cracks with only 5 millimeters machined off the surface. So here we have this extremely expensive steel with cracks 50 millimeters long in it. It's very difficult to find the cracks because they're very thin. They were put in vacuum, so there's not that much oxygen. So the bifilms are extremely thin, so you can't find them, but they're still very efficient cracks. And here is one of these cracks. Look, 60 millimeters long. This is the thing under the microscope. It's a very messy sort of crack. This was observed by people at Cambridge University when they bought a bit of steel, and they bought the best steel they could afford, thinking it was going to be free of defects, and they found this 60 millimeter crack in it. Just totally remarkable. And here we are. I don't know whether any of you have been around helicopter building operations. They're truly amazing facilities. This is one I haven't seen in Brazil, but I've been around others in the world. And the helicopter people go to a lot of trouble and spend a lot of money on getting them as right as possible, and who wouldn't? However, they are victims of us as misguided metallurgists making steel with cracks in it. And when you look at over the years, just of the last few years, the last decade or so, from 1977 onwards, practically nearly all of these mechanical failures are vacuum arc remelted steel. And what's quite interesting is that these 2012 failures, when these helicopters, these Pumas, ditched in the North Sea, fortunately no one was killed because they landed nicely and the floats kept the helicopters afloat. But both of them failed from fatigue failures from corrosion pits, which, as we know, is not possible because the corrosion pit is too small to initiate a failure. And none of the world's experts could understand why these had failed, because the failure was impossible from a tiny, tiny pit. And these, many of these gearbox and the main drive shaft parts are made with things like safety factors of 5. I mean, they're not lightweight components. They're built with enormous strength, and they still fail. And it has to be that they're failing from the vacuum arc remelted steels with their bifilms up to 50 millimeters deep. And this one too, this very tragic one in Norway in 2016, when 13 people all died there. And again, this was again from a corrosion pit. No one could understand how you could get fatigue from a corrosion pit. But as soon as you realize that the pit is a sign that there's a bifilm underneath, then you realize what's happening. So these are very tragic, many of them. Nearly every one of them is a bifilm problem. And this contrasts with the much lower cost material, electroslag refined material, which is frankly pretty good. Even this isn't as good as it could be because lumps of the electrode fall off, because the electrode is very often top poured. I don't care that it's poured in vacuum. We still create bifilms in vacuum, so this thing has great cracks through it. And so every now and again, a part will fall off into the melt, give a massive defect. So even this excellent process, we're doing it badly at the present time by casting the electrodes badly, which puts faults into the ingot, which need not be there. This could be an excellent process and could be the world's first reliable process to deliver a reliable steel. The first and only one, and we're messing it up at the present time. But it need not be messed up, and I look forward to the day when it is. So, just quickly having a look at where we are in metallurgy. Atoms were discovered in about 1900 and explained strength and rigidity. Thank you, Sheila. Then we got people realized that there were vacancies, which gave us point defects, and suddenly we could understand diffusion. And then we got line defects. Suddenly we could understand plasticity. And I like to think that now we've got planar two-dimensional defects as biofilms. And for the first time, we can understand fracture. So here you are, chaps. This is the unashamed self-promotion, but I do recommend my books. I like to think they will help you to get good castings. And finally, if you're really interested in all the details about fracture, which we've talked about today, it's here in my book. And you need a big block of ice on your head as you read it, but I'm sorry about that. But it's interesting reading, and it's different. But I wish you luck, and hope that in years to come, we're going to get better castings with fewer defects, and we're going to have safe engineering constructs. Best of luck. Thank you. Bye.
Thank you, John. That book I can recommend to everybody. I pick it up and read it over and over. And I said to John at the beginning of this that I was reading the preface to this book, and I'd recommend it to anybody. It really sums up this whole presentation and the whole book. And I was hoping you were going to make the, when you were talking about like that picture on the front cover that, you know, people believe carbides are brittle and they crack under stress. And in your preface, you used the analogy of a rounded pebble from the beach.
Oh, yes.
I was hoping you were going to use that.
Well, I forgot about that.
Yeah, well, I guess
Yes.
the analogy is that the rock is like the carbide and the butter is like the microstructure around it. And
Shall I explain that for the benefit of listeners?
Go.
That what I say about this is we can understand this problem if we pick up a pebble from the beach, a nice rounded pebble, and inside a block of butter, and then you were to shear the butter. The question then is, would the pebble break? Well, the answer is, don't be ridiculous. Of course the pebble's not going to break. And so here we are as metallurgists with talking about carbides in steels. The carbides are enormously strong. And I mean, far, far stronger than the steel, as we all know, because we use them as the points of our cutting tools when we're cutting hard steels. I mean, it's so the question is, will the carbides break when we stress or shear the steel? The answer is no. They're far stronger than the steel. And what's going to happen is the steel is going to deform around them. So the fact that they are cracked has to be some other explanation. It's not due to stress, and it's simply due to the fact the carbides precipitate either side bifilms, and actually by doing, as I say, these accommodation of the shape changes and the volume changes prise open the bifilm, and just the two sides of the bifilm move apart a little and reveal the crack. And interestingly, we haven't talked about hydrogen embrittlement today, for instance, but this business of the cracks being opened by precipitates is precisely what's happening in some forms of hydrogen embrittlement. That the bifilms are filling up with hydrogen and providing routes through the steels where hydrogen can now flow easily, because we've carried out heat treatments which have precipitated these carbides, prized open the bifilms, and now the bifilms are wonderful kind of motorways through the system for the diffusion of gases. Anyway, so there's much else in the book. Stress corrosion cracking is something else that we can explain for the first time. So it's very exciting that suddenly we can understand fracture, whereas previously none of these things like hydrogen embrittlement, stress corrosion cracking, there are no good theories for those. But as soon as bifilms come on the scene, suddenly the explanations fall into place.
Thank you, John. The questions have started. Murray Brown has kicked it off. He wants to know where can he purchase that book. Maybe I could help because I've purchased it. But it's published by Elsevier.
Yeah.
Correct. So if you were
That's
to Google in that title and go to Elsevier, they'll encourage you to buy it. There was some discounts for pre-publish purchasing. Interestingly, in a conversation I had with John, I said, when I looked on the back cover of my book, it said printed in Australia. I thought that was interesting. So John got his book off the shelf and it said printed in the UK or Great Britain, one of the two. So I guess what they're doing is they print them locally. They just send them the digital and they're printed locally. So there you go. The book is printed in Australia.
Interesting, isn't it?
So go out there and buy it. It's well worth it. You'll be able to tell your grandkids that I remember the day when metallurgy changed. Others are being a bit cautious with their questions. Get in there. I'm sure you've all got lots of questions. I've got a page of them here, but I'm reluctant to start on them until you've all had your go. They're still reluctant, John.
You better start then, Gary.
Yeah. Early on, you were saying that precipitates form only on bifilms.
Yeah.
And that begs the question, okay, if we don't have any biofilms, what's the microstructure going to look like?
Yeah, that's a very good question. No, I'd be really interested to find out about that. I mean,
well, you have speculated about the aluminium silicon system, that if there weren't any biofilms, you would get the modified silicon structure.
Yes, and that actually is known, and in fact, there has been some research, particularly in China, of a young Chinese out there who looked at aluminium silicon alloys straight from the smelter before anyone had had chance to mess them up. And what he found was that the modified silicon extended right up to about 16% silicon. And in every case, it came out as a eutectic and would have continued, except that he then raised his silicon by adding lumps of some higher silicon master alloy, which was full of bifilms, and that wrecked his experiment, which of course he didn't understand. So we thought there might have been a limit. I don't think there's a limit, that without the bifilms, you can't precipitate the primary silicon. It can only grow as a eutectic. Yeah, so that's an interesting example.
Gee, they're all really quiet tonight, John. Nobody's coming forth. It even surprises me.
I'm coming.
Well,
Somebody wants to voice it. Is it Bala?
Yeah.
Is it?
Yeah, it is Bala.
Go.
Yeah, look, you touched based on hydrogen embrittlement. Does it mean that more bifilm, more hydrogen could accumulate?
I'm not sure I heard the first part of the question, but let me answer what I think you've asked. Now, there's a lot of background here, which I'll try to summarize. People have recently tried to control hydrogen embrittlement by providing microstructures which have bigger and better hydrogen sinks. And so there's some recent work being done at Cambridge where the people there have selected some special carbides. I think there was a tungsten carbide. I can't remember exactly what carbides. I think niobium was another one. But these carbides had big displacements in the matrix when they formed, and so there was a lot of dislocations formed around them because of the accommodation with the matrix as they plastically worked the surrounding matrix. And it was thought that those strain fields and the population of dislocations would be better sinks for hydrogen. So this particular steel would be able to absorb more hydrogen without the hydrogen forming itself into cracks, because it was simply disappearing down into sinks. Now, this is potentially a very interesting and useful idea. But what I think their precipitation reaction is really doing is they're precipitating their very special carbides, which make big volume changes. They're precipitating them onto bifilms. And by doing that, they're prizing the bifilms open even more. So now the bifilms are even better sinks than they were before. Now, this is not the world's most wonderful solution, simply because you get some relief from the hydrogen for a time. But you can see what happens is the hydrogen, as it flows into the metal, first flows into the sinks, which in my view are the bifilms, prized open by. But once the sinks are full, and the sinks then start to increase in pressure with increased hydrogen precipitation, when finally the pressure reaches the yield point of the metal, at that point now, the metal starts to give and the cracks start to extend. And before you know where you are, you're into a situation of increasing hydrogen embrittlement. And so the sink concept gives you some relief for a start, but no relief in the longer term, and possibly makes it worse in the longer term. Now, I don't know whether I've made that clear, but you can see it's not the simplest of processes. Yeah, I don't know whether that's answered your question.
I've muted you, Bala.
Yes,
Oh, you're back.
yes. It answers the question.
Oh,
Okay.
good. Thank you.
I'm going to mute you again, Bala. Kim in Queensland has asked the question, and it often comes to my mind. It relates to mechanical properties and what's achievable if you can get rid of all of the biofilm. So Kim's asking, what's the best iron alloy mechanical properties you've seen that you can attribute to less or no biofilm? What's the level that we can say is potentially possible?
Well, I can answer this at two levels. One is just in the foundry, and many of you know of Bob Puhacker, a good friend of mine in Canada, who is using my concepts to make, frankly, some beautiful castings. And he started off in steel castings, and there was, I forget the particular steel alloy he used one day to make some customers their castings. And normally this would have had about 45%. And because he'd done a very nice job of casting these things, they had 75% elongation on that morning. And the customers refused to believe it because this had never happened in their steel before. So there are, shop floor instances of steels improving by factors of 2 or so. But if we look back into some little known metallurgical history, I forget who it was, which I report in my book.
Is that on the
Looked at these were the tensile testing of extremely slim whiskers of steel, which were so small that they couldn't. There was no chance they could contain a defect. And so when these were pulled, they went up to enormous stresses in the gigapascals. But when they finally fractured, they fractured by disappearing into a puff of smoke. There was no specimen left. And the puff of smoke, rather surprising, but the explanation is that now we're stressing materials and separating atoms in the same way that explosives separate atoms. That you, by separating atoms in this way, you generate enormous forces and release enormous energy. And this is what happens when we don't have stress relieving features in metals, but the metals go up to their theoretical stresses, and then when they do break, they release these enormous energies, which are the same energies as we see in explosive materials like TNT. So yeah.
Kim, I guess what you could expect is near to the theoretical strength, and I think for an iron alloy, that's what, 30 to 50 gigapascals?
Yeah, absolutely. Yeah.
Okay.
Yes, it's a big bang when it goes.
Yeah. They had a loud explosion, and then there were only whiskers that were micron thick or something.
Very thin. Yeah.
Chris Buck said goodbye. He has to go. Kieran asked the question that if primary aluminium smelters are adding biofilms into pure aluminium, just in the process of tapping metal out of the pot rooms, and then transferring the liquid metal into alloying furnaces in their cast house, can these biofilms be removed effectively at later processing? I guess he's referring to the later processing being at the foundry, where you do your castings.
Well, okay. Yeah, I mean, these are very good practical questions. You know, what are we actually going to do in our foundries? And there, again, if I refer back to my good friend Bob Puhacker, he's carrying out a procedure I recommend, which is and I'm talking solely about aluminium alloys now, in which he encourages the precipitation of biofilms by precipitating out on them the grain refinement precipitates like titanium and boron. And these make the biofilms heavy, and they then drop out of suspension. And I must say, Bob's developed a good technique, which I haven't ever asked him as a matter of fact, because this is some of his own technology, which I don't like to feel I'm stealing in any way. So I don't know the details, but the principles are clear that this is a sedimentation technique, which he's got devised now to be extremely good, because he's getting routinely now elongations in his A356 alloy, typically 18 to 22%, and I think he's on his way to getting up to 20% elongation. He's all the while improving his technique. So, these things work in an average foundry. I personally have been involved in quite a different approach. I say quite different in the sense that I'm wanting to build the sedimentation technique into the processing. And I'm helping a foundry in England at this present time, setting up a new foundry arrangement whereby we never pour any metal. So we never generate any biofilms, and we precipitate out those biofilms which arrive in our incoming metal. And so that sedimentation technique we're building into hardware such that you press buttons and it happens. And I'm very hopeful that we're going to be successful with a prototype foundry sometime early next year. So that's an ongoing process. Having said all that, there is a fair amount you can do with filtration. Filtering isn't perfect, but it's a lot better than nothing. And again, if you don't use the filter in the direct impacting way, I mean, how to explain this? If you have a runner and you put across the metal, so the metal hits the filter and goes through it and continues along the runner, this is the worst way of trying to filter and is next to useless, because it's going far too quickly through the filter, gets almost no chance. You're hammering inclusions through the filter. In fact, possibly generating inclusions at the back of the filter, because the back of the filter, you've got jets, separate jets coming out of separate pores, and around each separate jet, you have an oxide film. And so you're generating oxides downstream of the filter. It's the worst scenario. So don't do that, okay? Use my technique of using the filter parallel to the flow and let the flow go by. Let the flow take the energy out of itself in a spinner. Always use a spinner. Don't use any other kind of trap. None of the other traps work. A spinner works. And it works because it centrifuges all the bubbles, all the oxides get centrifuged into the center, which means that they can't reverse out into the runner again, which all the other traps, all the other traps empty once again. Having filled up with all the rubbish, they then regurgitate all the rubbish back into the running system. So do use a centrifugal trap at the end of the runner. And the great thing about that is that it increases the back pressure by slow degrees as it fills. And in that way, you put the metal slowly through the filters, which are now placed flush with the runners. And the metal now goes through the filter slowly. And now it really filters. And what's more, the metal doesn't jump and jet out of the back of the filter. And with luck, well, with proper design of the filling system, you can submerge your filter with sufficient level of metal that you suppress any jetting or fountaining from the filter when your spinner finally fills with metal. And it goes bang, the metal comes up to the top of the filter, and now we get the full head pressure from the sprue. And now we get the full rate of filling of the mold, so we can meet our target fill times. So if you really want your mold to fill in 4.5 seconds, you can do it, but you needn't jet through the filters. Now, best of luck.
Thank you, John. I'd like to add a little bit to Kieran's question, because I think there's great potential in smelters to make better materials for foundries to use. And look and listen, read what John's talking about, and I'm sure there's a market out there for a primary aluminium smelter to provide perfect quality ingots. It would make the life of the foundryman a lot easier. There you go. There's a challenge, Kieran. If you want some help, give me a call. A question came in from Christoph. This is Christoph Hartmann from Fraunhofer in Germany. He joined your first presentation. And Christoph's doing some experiments there in Munich at their lab with your techniques. He's bought your books and he's trying to get the researchers. It's hard to change them because they're all set in their little research bubble areas and their way of thinking, but he's trying. So Christoph asked, do you think sedimentation is the most effective way to remove biofilms from melts?
Well, it's a good question, and I think the simple answer is yes. And it's yes because it's the one process over which you've got some kind of scientific control. You can get your temperatures right to get the precipitation you want. You can give it more time by designing your system such that you can precipitate out to smaller sizes. And for instance, the way I'm viewing the building of our hardware is that we have a continuous flow of metal, and as it comes through our sedimentation unit, I give it just sufficient time as it goes through the unit such that it will precipitate out inclusions down to about a size of 10 microns. Now, the size of 10 microns is interesting in the sense that this is the size of a typical inclusion. It's a kind of dimensions of a order of magnitude of the arm of a dendrite. So it is the sizes you see in the microstructures of metals. And my thought about that is this still important? And it may be that the 10 micron size of biofilm is still going to influence properties. And maybe I should be targeting 1 micron. But the great thing about sedimentation is that, okay, I'm now going to change the parameters. I'm now going to give it longer. I'm going to change the temperature to get more driving, thermodynamic driving force, to get more precipitation. I'm going to change the instead of titanium, which isn't that heavy, I'm going to move to heavier metals, tungsten, molybdenum, such that now we get more weight on the biofilm to take it out of solution faster, etc. I might even do a pre-filter such that I take out all the big biofilms first and I'm only left with the fine ones, so the fine ones have got a free fall. Now, so there are lots of features I can build in to target different levels of residual defect concentration and defect size. So I say, yes, I think sedimentation is potentially a good way. That doesn't rule out other ways like filtration. And maybe filtration is or could be engineered to be better than it currently is. What is certain is that at the moment, filtration is generally engineered extremely badly and puts through huge quantities of inclusions. That's if it doesn't generate inclusions itself. But it's got potential. And I think that up to now, I haven't seen its potential used, but if you would like to go that way and test it out and tell the world that that's the best thing, I'd be delighted. Saves me a job.
Thank you. There's a challenge for you, Christoph. Maybe we can talk about it one night when you call me. Murray Brown is brought up. He's saying he's just remembering that there's an oxide film all the way around the surface of the ingot, like you explained, them as newspaper size. And so how do you control that impact on final metal quality? And I think you answered that last week about the dry hearth, but I'll hand that over to you, John.
Okay. Yes, in my early days when I was building the Cosworth process and getting that running, we overlooked the fact that everything we added had its own oxide film on the outside surface. And very often, if these were ingots or returned castings, scrap castings, our own foundry returns, these oxide films on the surface were very severe oxides. They were like pieces of leather. And of course, they were the same shape and size of the material we were adding. And so these are very substantial, massive, strong and huge oxide films. And of course, as these ingots or castings went into the melt and slowly was submerged, you'd have the melt rolling up against the surface, again with its oxide film. And so as this went in and the new oxide rolled up against the other oxide, we were creating a bifilm, a massive bifilm of the size of the chunk of material we were trying to melt. So this was a way of filling the melt with bifilms the size of newspapers. And what's more, a thickness, which was a thickness like a piece of leather. So, and I say in the early days, no one thought about that. And we did have, on occasion, some horrific defects, which only slowly we realized we were adding these what I now call the primary oxide skins on the charge. I call these things skins now rather than films, because they are somewhat different. They are horribly thick. Anyway, nowadays I see as the only sensible way of melting, I see as being a dry hearth furnace, in which you throw stuff into what amounts to a shaft furnace. You put stuff in the top, it comes down the shaft as spent gases are going up the shaft. So we have a counterflow heat exchanger, which is very efficient. So it's very effective and efficient in use of energy for melting. But the final melting takes place on a dry hearth. It's a slightly sloping hearth where the melting takes place and the ingots and the castings sit on the hearth. A little hole appears somewhere in their oxide skin, and the liquid metal drains out of the skin, which then sits on the hearth. So these skins pile up on the hearth until they're a great heap of oxide skins, but all the liquid metal has drained out of them, has drained down the slope of the hearth and into the liquid bath. And every now and again, you open a side door, scrape out the skins into a skip, close the side door, and you continue melting. But it's a magic way of separating your liquid metal from the primary skins, and the two go two separate ways in the melting process. And that contrasts with all the other ways of melting you can think of, like crucible melting, where everything goes in. And when the primary skins go in, you've then got to get them out before you cast. And this isn't so straightforward. And the huge bath furnaces you see in aluminium casting shops, which have 20 tons of aluminium, in which they just ingots and spent castings are all thrown in and mixed up. The thing's a disaster. There's no way to get out those primary skins again in such a vast amount of metal. I mean, our metallurgy at the moment, our metallurgical processing as an industry is dreadful. We've designed everything about as badly as we could. So, I see this as being a very serious problem in the industry, and giving us serious problems with the kind of metals that we really want and we really need. And we're going to have to do an awful lot of rethinking. Anyway, that's where we are.
Thank you. Alan Cook asked a question of myself, and he's asked if at CSIRO in our Lab 22, which is the 3D printing lab, and there I look after the 3D sand printer. He's asking, have we produced any molds, sand molds, using John's methoding principles, particularly the spinner trap? And if so, what improvements in properties did you find? I won't spend too long on this. The short answer is yes, we have. And it's my aim to prove that first at CSIRO, casting aluminium. And then I'll make those molds available to any foundry that wants them. And you pour your metal the way that you treat it, and you can pour it into your standard Australian standard test mold. I've even got I can print them for you if you haven't got a pattern, an E-type mold, and then pour it into John's mold and see if you get any different results. If you do, then it's due to John's methods. It's a good way to quantify it. maybe I'll leave it at that, and this will be a topic for further discussion throughout the AFI later on.
Can I add something to that, Gary?
Yeah.
Just to say, I use printed molds a lot, printed cores all the time these days. I mean, it's the printing process is valuable to the founder, and I'd recommend everyone to get one. I find them really useful. However, when you say, you know, you need one to put in my systems, hang on a minute.
No,
this
you
isn't
don't.
true.
No, I didn't mean that.
Yeah.
No.
Anyway, no, I mean, there's dear old Bob Hacker who's just running his foundry in which everything is molded, and so that his molds, and he's got big, complicated castings. So generally his molds have at least 2 or 3 parting lines. You know, they're at least 4-piece molds or 5-piece molds, but that's what he has to do to get out his castings. But in the meantime, he's also putting in and taking advantage of that and putting in very, very good running systems, complete with the spinner, the tangential filters and all the, you know, the features which make for good castings.
And they're all in John's mini casting handbook, 2nd edition. The previous slide, John. Sorry, I didn't mean to imply that you've got to use 3D printing. It's just a convenient way for me because I can make quick changes to the mold, try a spinner, try this, try a filter, and once it's settled and I'm happy with the design, then somebody can make a pattern and you just make them in your foundry. Otherwise, I'll print them and give them to you. David's asked a question. For clarity of biofilm removal, would be, okay, he's saying the biofilm removal technique would be material dependent because it depends on the density, right? And I think you covered that last seminar where, you know, aluminium, there's likelihood of neutral buoyancy, whereas in ferrous alloys, they're lucky because they all float out and etc. So maybe you could talk to that or answer that if there's more.
Yeah, it's a good point. I mean, it's only aluminium and magnesium where the biofilms will sink. And for instance, in magnesium, they're so heavy compared to the very light liquid metal. And very often one is doing these, is it zirconium or whatever it is, the grain refinement bioflux technique. And that's almost certainly a technique in which the flux is made heavy by, I think it's barium additions, and it sits on the bottom of the melt, is stirred in and continues to sit down at the bottom, and is doing a job of actually absorbing biofilms. As biofilms arrive, they're just taken into the liquid flux. And so what appears to be an alloying effect of zirconium, which puts up properties, I suspect it's merely a cleaning process. And you've got a cleaner alloy free from biofilms and therefore got good properties. So magnesium and aluminium, the biofilms go downwards. In every other metal system, they float upwards, and you have to encourage the flotation upwards. And so, for instance, steels have good elongations, like typically 50%, simply because the flotation process has been very good, and particularly if it's been continuously cast, because the liquid metal sits on top of the continuous casting machine for quite a long time, giving the chance for flotation out of inclusions, while the ladle is continuously feeding the machine with liquid steel. So that particular steel casting process can give really quite good results, and gives, as I say, steels with 10% elongation. And there are steels with even much better elongation than that. I don't really want to get into that now, but that's because they've got liquid surface oxides. So when you fold over these surfaces, it's liquid oxide to liquid oxide, and now you don't form bifilms, and you just form liquid droplets of oxide. So what is it? Trying to think of it's the high manganese steels, which are very successful, together with the high boron steels. These are the steels which seem to benefit enormously from liquefying the surface oxide. But
Hadfield steels, is that
Yeah.
what you're looking for?
sorry?
Hadfield steels, is that what you were looking for?
No, this is a new steel. It's the it'll come to me in a bit. But
Right, yeah.
what I was going to say was that a lot of the steels have relatively poor properties, simply because they're cast so badly, and they're cast by pouring into ingots, and very often it's top pouring, but even the bottom filling of the ingot, which you call uphill teaming, this is still very, very bad, as we saw in the lecture last week with the air entrainment is unbelievable, horrific. So our processes at the moment are designed to make very bad, if not the best they do is make mediocre materials. But it need not be the case. And for instance, if we look at bronzes, like the aluminium bronze, that has a reputation of being very difficult to cast, but only because it entrains its own oxide film during turbulence. And if we cast it by, say, counter-gravity techniques, we can get wonderful castings with wonderful properties and complete freedom from defects. And there's a huge scope out there for foundries to revolutionize what they can do with, and particularly for things like cast irons and brasses and bronzes. These are materials which the metal temperature is not that high, and you can easily set up a counter-gravity system. What I am admiring Daimler-Benz for in Germany at the present time is that they've set up a very nice system in which they're making steel castings by using a pressurized furnace. And good luck to them. They're pioneering a new way there of counter-gravity casting of steel without the use of a riser tube. And the standard formulas for counter-gravity casting with using riser tubes becomes difficult for steels, because you just can't get decent riser tubes. And say the Germans have now done it very successfully and are making some very nice castings in a very productive machine. So good luck to them.
Thank you. Kieran has come back with a statement and asking your opinion. I might take this as the last question as well, John. Kieran is saying that he believes that as a primary aluminium smelters have been pressured to automate their processes to offset costs. A lot of industries have been like that, haven't they?
Sure.
They've adopted more mechanized degassing processes, etc. But they have gone away from manual or mechanical skimming of ingots and adopted underpouring techniques in casting of ingots that may not be as effective in removing biofilms from alloy ingots. Anecdotally, casting from primary alloys are not as good as they used to be when ingots were skimmed. Secondary aluminium alloy ingots of the same alloy types that are skimmed reportedly or purportedly produce better castings than the primary versions. Do you see some sense in this proposition? So I guess he's saying that now they don't skim, but I think the problem's deeper than that, but I'll hand it over to you, John.
Well, I think it's the answer is definitely maybe. God knows what he's saying, because the way to keep out the production of biofilms is subtle and depends on the details of the process. Whether skimming happens or not seems to be almost irrelevant, in the sense that what's going on beneath the surface is what's really important. And by not skimming is the implication that the surface oxide and dross is being entrained during transfers. Now, I don't know that. That's a detail. And there's no reason not to leave the dross on the surface if it isn't doing any harm and it's actually protecting the melt underneath. But if there is danger of entraining it, then perhaps it should come off, or there should be barriers, or there should be filters. I mean, the whole thing needs to be looked at as an integrated system, and every detail has to be correct. And then suddenly you get wonderful properties. But you only get a tiny part of it wrong. And this is the really cussed nature of our liquid metals. You've only got to get one tiny detail of the process wrong, or you do a beautiful running system, but just on one corner, the corner was just too sharp and you entrained air, which you didn't know about, but it wrecks the casting. And as I say, that our metals are hypersensitive. So, this is why gravity pouring of metals to get good castings is not straightforward, and it's not efficient. And say gravity is doing us the disfavor of accelerating our metals to speeds we don't want and giving the metal sufficient energy for it to jump and splash, which we don't want. But no, it is controllable, but not easy to control. And so the design of a controlled system is, you've got to be very, very careful with it. And I'm sorry about that. My recommendation is don't use gravity to make castings. Go to counter-gravity. And then you don't need a running system. You just drill a hole in the bottom of the mold. You just fill up the mold. No problem. You won't get it. Abandon running systems. Now, there's a recommendation for you.
That brings back memories of your 2012 Hoyt's lecture at the AFS.
Oh, yes.
Stop pouring,
yes.
Start casting.
Yes. Yeah, that's right.
That was a great one. I like that. So thank you very much. I'll call the questions to an end. And if people want to stay on and have a bit of a chat, maybe John could stop sharing his screen and then we can chat. But Amber wants to wrap it up. And thank everybody. Thank you, John. And make a little bit of an announcement. So over to you, Amber.
Well, yes, thank you, Gary, and thank you, John. You've been so generous with your time over these last two presentations. Cannot thank you enough. I speak on behalf of everyone who's attended, and I'm sure there'll be more questions in our open chat. But for now, we've had a few questions from the beginning of this SOFA seminar series. We said that we would be sharing the presentations because we're recording them, and also we would make available the slideshows. So I just quickly want to share the screen. We've been working with our website hosts in getting them to put up our presentation, our SOFA seminar series and the presentation. So I'm just going to share my screen with you so that you can see what we've got. So you can see here, if you go into the AFI website, the main website, it will take you straight to the homepage. Just type in australianfoundryinstitute.com.au. That will take you to the main page. And then if you go across to the Victorian division, you will be able to scroll down and see this banner here that says AFI Vic SOFA Seminar Series 2020. Very soon, because they're working on it as we speak, each of the different SOFA seminars presentations are across the top row, and then along the bottom row will be the PowerPoint or the slides. So you will just be able to click on to the first one. A flyer will come up. It will have a YouTube link in it, and you'll be able to click on the link and then watch each of the presentations. And if you like, you can split your screen in two or have two screens. You can also go through the slideshow simultaneously, but it's not available at this point in time. I have checked prior to tonight. It won't be far away. They're currently working on it. Tonight's presentation, number 4, will also be available, I would suggest, in the next few days. Once we get it edited and we forward it into Yellow Pages, they will get it up and running. So it will be accessible. We may flick out a little email reminder when we know it's live, so that everyone knows that they can log in. Just before I leave, Kimberly has asked if she could possibly say something very quickly about the 2021 conference, because that is the traditional way that we end a conference. So I will hand over to Kimberly very quickly. You need to unmute yourself, Kimberly.
I unmuted you.
Thank you very much. Sorry, I changed onto sharing and I lost my functionality. Thank you very much, Amber, for giving me this very quick chance to share. I'd just like everyone to save the date for the 28th to the 30th of October next year. We're planning an in-person conference right on the banks of the Brisbane River in the CBD on South Bank. We've got the theme, Don't Stop Thinking About Tomorrow. So anyone who's a fan of Fleetwood Mac or Foundries, welcome. There's going to be a lot of playing of that song, I imagine. Just as a quick introduction, the Thursday night we'll have the President's Reception. Friday we'll jump into a full day of conference itself with our friendly, instead of golf, we're going to go do 10-pin bowling in the CBD. Full pizzas for everyone, open bar. It's an optional, but it's definitely recommended. Saturday we'll jump into a full day of conference again, closing with the conference dinner, again in South Bank, beautiful views, lovely day. And Sunday you can wake up late and make your ways home or spend some time in our lovely city of Brisbane. So we're really hoping that you'll all come along next year, and we'll be in person and get all the benefits of that as well. So thank you.
Thanks, Kimberly.
Cool.
Yep.
Okay. So
Thank you.
I think now I'll hand it back to you, Darren.
Yeah, people are sending in their congratulations and thanks. John, great presentation. Thank you very much. And thank you to AFL Vic for putting it on. I think Amber, myself and Alan and Murray will be quite pleased at the end of tonight, because it comes to an end of a very long, almost a year of setting up the first conference in Christchurch, and then that stopping, and then considering Melbourne, and now this. And even this is not that simple, by the way. And Amber has been burdened with a lot of the stuff, so thank you very much. I just push buttons here and speak a few words.
Oh, Gary, do not underestimate what you have done in your assistance. When we've had many SOS calls with me to Gary going, what do I do here? So it's been great. So thank you so much. Your help is fabulous. Thank you so much.
Oh, Brett Lawrence from Intercast said thank you. Thanks for joining us, Brett. I didn't see your name on the list. So yeah, if anybody wants to have a general chat, but it has been a long night, and you know, John's been talking for 2 hours, and the tea helped a lot. But he might be getting near the end of his voice, and I found it really great. I can't encourage you enough to really read that new book, Mechanisms of Metallurgical Failure, The Origins of Fracture. It'll turn your thinking upside down, like John said. The world's been thinking of it wrong. And I think, this, like I said earlier too, this marks a point in time where there's going to be a change, and it's not an overnight change. This is going to be very slow, I imagine, and engineers are very reluctant, and they want proof and more proof and more proof. But as John says, the castings have got a bad reputation, and they can be made a lot better. And I don't want to be critical of the foundries in Australia, but I see lots of opportunities for improvements. Just adopting John's methods, you can go a long way. But like one of the questions last week, why do it? And there's lots of reasons to do it. Just think about it. Roger Lumley came up with a really good point that for some reason I just didn't think about. If you adopt John's methods and you make really clean castings, then your runners, okay, they're a smaller weight or volume, like John said, but your runners are good material. It's probably better than the ingots you buy from from the primary suppliers. Is he gone?
No, still
okay.
here, and he heard every word.
So your internal return are excellent quality metal. This is a big plus for you, all right? Maybe John knows all about this. And just get rid of the big sort of leather coat skin around them, and you'll be fine, right? You're starting from a good beginning. And so that's another benefit. So there are lots of benefits. Oh, Kim, yeah?
I guess to follow on from that, John, I was going to ask, has anyone mainstream adopted this as the original way people teach about mechanical failure? You know, has any university swapped over to teaching the brand new engineers that will make the difference this method straight from the beginning?
You're muted, John. Yep, that's it.
Yes, Kim, thank you for the question. It's a very relevant question. Gary's right. Things are happening very slow. But and so when I do hear about people starting to teach my systems at universities and technical colleges, it's kind of very welcome news. And so it's only recently I discovered that in Wisconsin, this is now in the syllabus. So that little patch of America is starting to use the technology and to teach it. And incidentally, it has got a big fight with the American Foundry Society, who are definitely not teaching it, and they're still teaching the old ways. And in fact, are still implying that they're in denial, really, that biofilms exist even. So the American Foundry Society, I think, has a long way to go. And the great pity, actually, of that little bit of history is that just before COVID struck, the president and his assistant from the AFS were due to go to visit Bob Puha to see whether it really was true you could make good castings by this idiot of a chap in England called Campbell, you see. And they were due to go, and the week or almost the day before they were due to go, COVID struck and they didn't go. And since then, there have been terrible, well, there are lawsuits threatened backwards and forwards about whether biofilms exist or don't. And I mean, I'm glad to be out of it. But the situation in America at the moment is, pretty dire, I would say, except that this little bit of Wisconsin is actually teaching and using the technology. So maybe from a small start, things are starting to happen. And I heard that in South Africa, they were doing some work too. But it's very mixed. I mean, I have a lot of students in Iran, for instance, and I get more of my books sold in Iran than anywhere else in the world, would you believe? But the fact is that when they write to me about their casting problems, I have to write back and say, "You've got it wrong again." And so they're continuing to be in a mess with the technology. And so, although they're at least sympathetic, they are trying, and it's only a matter of time before they get their act together. So, yeah, so things are happening. And as I say, this little project I have in the UK now to make an aluminium foundry in which the technology is built into the hardware such that you press a button and castings pop out automatically, and they're automatically perfect. Now, this is something that the aero industry they can't wait to get their hands on a process that's going to be reliable. At the moment, none of their suppliers are reliable. They can't reliably produce castings on the day they would say they were going to produce them. Okay. So the world situation, we're in transition, I like to think, but the transition is going to take time. And in the meantime, I shall get more and more unpopular, and someone's going to take out a contract on me one of these days. Anyway, it'll be a fast way to go.
The person who loses the lawsuit about there not being biofilms?
Sorry, Mike, I missed that.
No, I said the person who puts out the hit on you will be the one who loses the lawsuit on the fact that there are biofilms.
Okay.
Well, as I say, I'm keeping out of all that so far as I can, and I've done my level best to pour oil on troubled waters. But it is difficult.
The casting temperatures that catches fire.
Gary, you'll have to translate for me.
Oh.
Yeah. Well, it's hard to translate, Mario. It's a really difficult one. Don't get him started, John. Just say yes. It's like with the.
Oh, I see. Yeah.
Just say yes.
Yeah, I'll do that. Okay.
I like your question, Kim, and it's. I want it to be part of the conclusion of my Churchill Fellowship, because the Churchill Fellowship is learn abroad and inspire locally. And so what I learn overseas, I've got to implement in Australia. And a part of that I want is the apprentice training. I don't know why apprentice training doesn't teach John's methods. What they're teaching is pretty old stuff. So look forward to that. And Wisconsin, is that a university course or is it a tech college? John?
It's the part of the University of Wisconsin, which has got more than one campus, and I can't remember where this is happening now.
Okay.
But this is a person, Kyle Metzloff, who's leading this work. He's an enthusiastic chap, and he has a number of students, and I envy these students. I wish I'd have had a teacher who had taught me castings as these students are getting taught. But he runs a fun sort of course, which I wish him luck.
I might follow that one up.
I believe he gave a presentation in New Zealand last year,
Did he?
2019.
Amber and Alan, were you there too, Murray?
Yes.
Oh. Okay. Oh. Did you get his card?
Don't recall. I'll have to go back to the records, Murray. I don't recall that name.
The guy from the university in America, I thought it was Wisconsin.
Yeah, I'll check it out.
Yeah.
He was quite dynamic, but I don't recall him being from Wisconsin. That's not to say that he wasn't, though. That's not to say that he wasn't, no.
Well, I think we've got the program somewhere. Amber, you should be able to pull that up pretty quick.
Not now.
Now,
No.
she's brain dead.
Been a big day. Yeah.
It has been a big day. I think we should draw this to a close if you think it's the right time. So I can't thank you enough, John. A lot of people you ask to do something like this, you just get a no. You've been very accommodating. Every time I ask something, it's always yes. And then when you give us more than what you said you were going to give. So thank you very much.
Great pleasure.
I really look forward to catching up with you in Ledbury next year.
Oh, right. Okay.
Ledbury's John's hometown.
Yeah, this is the centre of the universe. You realise, yeah.
Yes. Yeah.
But you'll realise that when you come and see it.
Yes. Yeah. I'm sure there's some good pubs around or places where we can sit and chat.
Wonderful. Yes.
All right. I need to correct myself. It was Iowa State University, and it was Frank Peters.
Okay. There we go.
There we go. Yeah. All right. Thank you, John. That was fantastic.
Thank you, John.
Very well.
Okay.
Yeah.
All right, guys. I'm going to stop the record.
Yeah.
Good night,
Thanks,
everyone.
Doug.
Thanks for
I
joining.
need to get going
Good
as
luck.
well.
Yeah.